Hello, Chem 1. At this point in time, you may have watched all the videos from Unit 8 and learned about all the different characteristics of covalent compounds. Today, we're going to take that information and organize it into the 8.6 chart to help us gain a better understanding of everything and how it fits together. Let's get started. The way this chart is organized is by domains around a central atom. So if you look over here to the right, the first one has technically no domains because there isn't a central atom, and then 2 domains, and then 3 domains, and so on. So let's start with the Lewis structure of hydrochloric acid. It would look a little like this. Some of these Lewis structures I'm going to go through pretty quickly for the sake of time. If we look at hydrochloric acid, the shape diagram is pretty much a straight line. Because there's only 2 atoms, we can only really draw this in one way. There's not really a bonded to lone pair ratio because there's no central atom. And the molecular geometry, because there are only 2 atoms, is linear. The bond angle would be 180 degrees, and there wouldn't really be a hybridization once again because there's no central atom. Hydrogen is 2.1 and chlorine is 3.0. That means that this bond is polar, and it also means that I can draw a line splitting the negative from the positive end, which means this molecule would be polar. So now we need to deal with the intermolecular forces. We know that all molecules have at least London dispersion forces as LDFs. And what that means is we can put LDFs in every box all the way down because we know that there will at least be temporary dipoles in every molecule, no matter if it's polar or nonpolar. But we identified this as a polar bond. That means that this will have dipole-dipole intermolecular forces. This is chlorine bonded to hydrogen, so we don't have hydrogen bonding. Hydrogen would need to be bonded to fluorine, oxygen, or nitrogen. So we just have LDFs and dipole-dipole. The next one we're going to do is beryllium fluoride. The way we would draw this, remember that beryllium is stable with 4 valence electrons. And because of that, there's no lone pairs around the central atom of beryllium. So if we take a look at this, we'd get beryllium with a straight line because there are no lone pairs. So this is 2 bonds to 0 lone pairs, which means that it's linear. It would be 180 degrees. And the hybridization, there are 2 hybrid orbitals around beryllium, making this sp. Beryllium is 1.5 and fluorine is 4.0. This would technically be classified as an ionic compound. That would make the bond polar. But because it's linear, this would be a nonpolar molecule, and it would only have LDFs. Carbon dioxide would look like this, which would be linear. There are no lone pairs around the central carbon, so this would also be 2 and 0 because it has 2 domains. The molecular geometry would be linear, which is 180 degrees, sp. These would be polar bonds if we subtract the electronegativities, but since it's linear and the oxygens are pulling in opposite directions, this would be nonpolar molecule, meaning this will only have LDFs. Now we have 3 domains. In the first one we have boron in the middle, followed by hydrogen. We have sulfur trioxide and sulfur dioxide. You can see based on these 3 drawings that they all have 3 domains, but it's kind of organized a little differently. In the first 2, we have 3 bonded pair and no lone pair. And their molecular geometry, because of this, is trigonal planar. In this last one with 3 domains, we have 2 bonded domains and 1 lone pair. That's going to give us a configuration of bent. If you have 3 domains, the angle is always going to be 120 degrees. And the hybridization would be 1 s orbital and 2 p. So the hybridization would be sp2. Boron and hydrogen make nonpolar bonds and therefore nonpolar molecules, and we'll have LDFs only. Sulfur and oxygen will have polar bonds but you cannot separate the negative from the positive, so these would be nonpolar molecules, and therefore only have LDFs. With sulfur dioxide, though, you have a polar bond. Because it is bent, it's also a polar molecule. This will give it LDFs and dipole-dipole intermolecular forces. Let's move on to 4 domains. Let's first draw these different molecules with 4 domains. I know my drawings are a little rough, but you can hopefully see that these are 3-dimensional tetrahedral structures. The first 2 have no lone pair. NH3 has 1, and H2O has 2. The shape diagram I've kind of already drawn over here to the left. So the first 2 have a bonded to lone pair ratio of 4:0. NH3 is 3:1, and then water is 2:2. So the first 2 would be tetrahedral because they're 4:0. This would be trigonal pyramidal because of the 1 lone pair, and water would be bent. The bond angle for all of these, because they have 4 domains, is 109.5. And the hybridization would be sp3 because there are 4 domains. The bond polarity for CH4 is non, therefore the molecular polarity is non, and therefore it would just have LDFs. For silicon fluoride, this would be technically ionic, meaning it's polar, but because it's tetrahedral, it's still a non-polar molecule, and therefore it's only LDFs. NH3, those are polar bonds, and that also is a polar molecule because we can separate the positive hydrogens from the negative nitrogen. That means this would have LDFs, it would have dipole-dipole, and it would also have hydrogen bonding because nitrogen to hydrogen is a bond that's taking place. Water would be the same. These are polar bonds. It is a polar molecule, and it's going to have all 3, LDFs, dipole-dipole, and hydrogen bonding. So now we can move on to the bottom ones, which have 5 and 6 domains. Your drawings would look like this, and these are going to have 5:0 and 6:0 because there are no lone pairs. The geometry here is called trigonal bipyramidal and octahedral. You don't need to know the bond angle for these, and we have sp3d and sp3d2 because we've added 2 d domains to the central atom. These are polar bonds, but non-polar molecules, and therefore they would both have LDFs, and only LDFs. So a good way to review the content from this section is to be able to fill out this chart and really understanding what's going on when it asks for bond polarity versus molecular polarity and what LDFs there will be based on that polarity. You also need to be able to identify shape and draw the Lewis structures for these different covalent compounds. Take time to practice this, keep up the good work, and we will see you soon.